Hello and welcome to the laboratory discussion for Laboratory Module 2. This is week 2 of the Introductory Geology course. And what we want to do in these laboratory discussions is to start with a review of the lab module before. That would be Laboratory Module 1. And after we finish the review, then we'll go into an introduction of the methods and principles to work with this next lab. This will be Laboratory Module 2. So today's laboratory module is on seismology, which is the instrumental study of earthquakes. Before we get to that, we are going to go to Laboratory Module 1 and do a review of visualizing the Earth's surface. Now, one of the things to understand about the reviews is we're not going to simply go question by question and answer the questions. The laboratory key with notes from the last laboratory module is always posted in the next laboratory module. So you will find on this laboratory module page, Module 2, a link to download a PDF file that has the complete key to last week's laboratory if you did the first laboratory. Now, we have a choice today in laboratories, and we'll talk about that as we get into the introduction to that laboratory. But let's start with our review. And to do this, I want to take you through the lab to two sections at the end. These are the culminating sections. So you go through a series of questions, working with maps, topographic maps, understanding contour lines, contour elevations, contour intervals, and I will refer you to the key to go through that. But the culminating part of this, do you understand it, can you work with it, are the last two sections. One section is referred to as working with topographic maps, or better, understanding topographic maps. And that section gives you a map and gives you things to do with it. And the second section that's culminating is constructing topographic profiles. So let's go ahead and move to the first section. And here's the map that you're working with in the part referred to as understanding topographic maps. It's a blank map and you're asked a number of questions. So what you're asked to do here is to locate the high and the low place, to look at the contour lines and the available information, and to figure out exactly what the elevations are for the index contours that have been left blank, using the index contours you have and the overall understanding of contour lines and elevations and topographic maps. You're also asked to plot a couple of streams. So we're going to go ahead and put the plot together for you. And this is what your map should have looked like once you got through it. So let's go ahead and go through parts of this. One of the things you'll note is in the breaks in the index contours, and those breaks are on purpose, right? The spaces were left so that you could fill in what the elevations were. You were given 4,000 feet and 2,000 feet. So in between the two, you should have written 3,000 feet as an index contour. Those are the dark bolded lines. And then you have 4,000 feet already filled in. And then going uphill, the next would be 5,000 feet, followed by 6,000. And the last index contour line that you have is 7,000 feet. If you go in the opposite direction, below 2,000 feet, you have one index contour show up, which is in the lower left-hand corner, or the southwestern corner of the map, and that's 1,000 feet. Now, if you look at a map like this, if you have 4,000 to 6,000 feet, there's 1,000 feet. Divided by 5, the contour interval for this map is 200 feet. Now you're asked a couple of things in addition to simply labeling the map. One is where is the high spot on the map and where is the low, and to put an H and an L. The L is below 1,000 feet in the lower corner, lower left-hand corner, and then in the upper portion of the map, about almost near the top, above 7,000 feet, you'll see that's where I put the H for the high spot. The high location, what do we know about it? The high is above 7,000 feet, but below 7,200 feet. How do we know? Another contour line doesn't show up. Now there's a wide space up there, so it's closer to 7,200 feet than it is 7,000. So if you were to interpolate based on the slopes on either side, interpolation in science is kind of guessing using the data, right? And it kind of rounds over the top. I would put the top of this hill at somewhere around 7,100 feet. Now, having said that, the other things you're asked to do is to note if you had an X on the map. There's not an X, but if you're in the lower right-hand corner of the map, that would be the extreme southeast corner of the map. What would you do if the area started to flood? You should run north. If you run to the west, east, south, you'll drown. Running north will get you away from the water that is rising. Why is that? Because you'd have an elevation change. You'd be going up in elevation in that direction. Now, the final part of this exercise is to find the two major streams. Now, there are a bunch of streams on here. They're all intermittent streams. That means if you go out there and it's a dry day and it hasn't rained in a month, you're not going to find any water in these channels. What you're doing is identifying the channels where water will run when it rains. And there are two major ones and then a lot of lesser ones. And so to find the major ones, you want the ones that show the biggest, longest channels. And I've mapped those in here for you. And one of them is in the center of this, and in the visualizations you can see a major canyon here. Now I want you to note that the beginning of this is, I think I'm able to use a cursor here to kind of show. So the beginning of this is up here near 6,000 feet, but notice I don't have it to 6,000 feet. It kind of ends where you start to lose the V. The V's are important, and by the way, streams can always be noted from a contour map, from a topographic contour map, as a place where V's are pointing uphill. It has to be the uphill direction, not the downhill direction. The downhill direction, you see there are V's pointing downhill. This is a ridge. You would not have water running. That would be at the top of the hill. That would be a violation of the law of gravity. You do not violate the law of gravity on any of Dr. D's laboratory modules. Not allowed. The water's going to run downhill in the low spots, and that would be in the channel. So up here, what would this look like? Well, this is an eroded area where the stream channel hasn't gotten there yet. How do I know? There's no V. The V kind of opens up. If you were standing right here, the channel would die right about there, and around you would be an area almost bowl-shaped where you had landslides and other modification of the surface because of gravity. The channel is mapped here. Notice how it is mapped through the apex of all of these V's. If you just draw a straight line like this, and some people do, they just draw a straight line because that's the easiest for them. Oh yeah, the channel's there, I'll just draw a line. Problem is, at times you have water running uphill, and again, you're violating the law of gravity. This is not done in Dr. D's laboratory modules. You may not violate the law of gravity. And the only way to do this properly is to take the time to draw the channel as I've done, going through the apex of all the V's. By the way, I put an arrow, and you were asked to do the same, right on the stream channel that you have mapped, showing the direction the water is flowing. That is downhill. The V's on the contour lines point uphill. The water runs downhill. The second one of these streams is a more straight line, is right here. It's not exactly a straight line. It is flowing to the southwest. It starts about up here, right? I mean, I could have drawn it just a little bit more. Somewhere right here is where the channel starts, and then it flows to the southwest from there. So those are the two major channels. If you can label the map with the proper elevations, if you can figure out the direction the streams are flowing, if you know which way to run if the place were to flood, if you know where the high and the low area is, you only need a couple more things to really understand topographic maps. For example, if you follow the cursor, this canyon, you're going up from the canyon here, you go up the hillside, that's pretty steep. If you come up the ridge from the other side, it's less steep. Remember that the steepness represented on a contour map can be seen in how closely spaced the contour lines are. The closer they are together, the more elevation you are gaining over a short distance. That's steep. The more spaced out the contour lines are, the less steep. So those are the questions that you should be able to answer, and we have an upcoming quiz on topographic maps. Can you read them? Can you understand them? If you can do these things, you can, and you should be able to ace that quiz. Now, the other thing you're asked to do in here was to do a construction of a topographic profile. This is an absolutely important skill set in geology for looking at landforms, because to understand landforms, it's not looking down at them that works so much for us, but being able to look at a profile across a landscape. Now, this has been started for you. The left-hand portion of this has been started, and it kind of walks through the steps. The first step is to line up your profile with a line of profile on a map. Now, this is pre-done. Everyone stop, time out. One of the things that's happened here is we've lined the two up for you. As demonstrated in the video I asked you to watch for topographic maps, that line could be in any direction. It isn't necessarily lined up for you. So in order to transfer the data of elevation from that line of profile on the map to your vertical profile, which is what you need to do to profile construction, use the edge of a piece of paper. Don't just draw it straight down, because if the lines are not parallel, you're going to get what we refer to technically in geology as garbage. It will not be an accurate representation, and that's what you're going for. So let's look at this. This is pre-lined up. Step 1 is to line up your profile with a line of profile on the map. Step 2 is to identify the elevations on the map that cross a line of profile. And you can see I've circled them. You don't have to circle them. I like circling them when I'm dealing with students so that they know this is the data we're going to transfer. By the way, where that elevation is positioned on the line of profile to that scale in the horizontal is going to be the same horizontal for your vertical scale below. The only thing you're doing in construction of a topographic profile is taking the elevation data along that line, and rather than representing them by the location of contour lines and the elevation of the contour lines, you're literally going to plot them to scale vertically. And that's what we've done here. Sort of step 3 is to then plot them. So you're taking the data straight down and you're plotting them. You have to make sure this is lined up with your vertical scale. Again, a lot of times you're not going to be able to do it directly like this. You'll have to use the intermediary step of taking the edge of a sheet of paper and marking across a line all the elevation points, then bringing it down so it's parallel to the vertical scale, and then plotting the elevation to the elevation line on that vertical scale. What you'll get is a series of points or X's. And that's what I've done here. Now note, it isn't a profile when you've put the points or X's in. It's only a profile when you draw the smooth line through. And I've done that for you. And the rest of it works out like that. Note at the high elevation here that I don't draw a line straight across. It's one thing we know isn't happening. Why? Because there's space between the contour lines on the map. So the elevations between those contour lines on the map are above that last elevation. So if this were flat, it would have to be flat above there. And I wouldn't draw it flat unless you know you're in an area of mesas and buttes. Here you're not. We use something called a constant slope interpolation. So the slope comes up from one side and the other side, and you just kind of gently round it in to give yourself a somewhat accurate visualization of what the landscape would look like there. Also note that the lines extend to the end of the profile. Even though your last data point is there, you kind of cause the slope to go out. You know it doesn't go below the next line, and you do that on the other side. It needs to go from A to A prime, or A to B, or X to Y, or Z to Q, whatever it is. But the profile line, and that's the smooth line that goes through the dots, need to connect from your beginning point, in this case A, to your end point, in this case A minus. So again, review the key, go over that. If you have questions, feel free to reach out to me. So that's what we did in the topographic map exercise, and we will have exercises later in the term, I think modules 4 and 5, where we need to be able to look at and read topographic maps and be able to construct topographic profiles. But let's move on to an introduction to what's going on in Lab Module 2, which is about seismology, the instrumental study of earthquakes. Now I want you to stop. If you have not watched the lecture on earthquakes, if you have not done that, then stop now, go back and complete the lecture on earthquakes, because this laboratory leverages things you know about seismic waves. I'm going to be talking about P waves and S waves and how they appear and how we can use them to understand things like the location of the epicenter of an earthquake or the magnitude of an earthquake. If you haven't done the preliminary work by watching the video lecture on this, then you're going to be totally lost. So again, if you haven't done that yet, you are to stop, go back, and then come back to this introduction. So let's go over the methods and principles involved in the laboratory. And you're going to be looking at seismic waves, and the two seismic waves that are important to us. We're going to not worry about surface waves. We're going to worry about the two major body waves. Those are P and S waves. And these waves go through the surface of the Earth, down in through the body of the Earth, and through the lithosphere, and back up, and they're recorded at the Earth's surface. Now, I just want to take a moment. We've talked about this in lecture, but there are some terms that come up, and we talk about it in lecture. I just want to go again. Seismic waves are the waves that are generated during an earthquake that propagate through the crust and lithosphere of the Earth. A seismometer is any instrument that measures those waves. A seismograph is any recorder of data coming from a seismometer. So it's a recorder of ground motion. It's a physical recorder. And the recording itself is referred to as a seismogram. So lots of seismos. But again, seismic wave are the waves themselves. Seismometer is the instrument that records seismic waves. Seismograph is an actual physical recorder to paper, a chart recorder of seismic waves, and it produces a seismogram. A seismogram can also be a digital production or recording. This is a typical seismometer. Does not look like much, but inside, modern seismometers have accelerometers that allow us to look at three components of motion. And that's the guts of the seismometer. And simply any vibrations coming through the Earth's surface will affect the accelerometers, and those will cause a signal, a current. That current is then digitized and sent to a computer for recording or sent to a chart recorder. In the old days, the seismometer and the seismograph were the same thing, and you could do that. You have a wheel moving on a clock drive, a pendulum with a weight, which means as the whole thing moves, the weight is going to be there. It's going to sort of stay stationary, right? An object at rest tends to stay at rest. It's one of the laws of motion. But what that means is the clock drive brings paper underneath the stylus that's on the pendulum. Then as movement occurs, it's going to record. And what you get is a recording of ground motion versus time. Now, this is a horizontal recording. We also had a similar thing going on with springs and a vertical recorder. And this is looking at vertical motion of the Earth's surface. Again, as things move, the weighted mass tends to stay in place. And as the clock drive moves underneath, you're literally recording over time ground motion. A seismogram is always a representation, right, of ground motion over time. Here we can see a chart recorder recording a seismograph. And here's the seismogram itself. It's a sample seismogram. Some things to look at, and I'll use my cursor to kind of show it. What's important to us is the first arrival of the P wave, and it comes through and we get some blip. And by the way, you can see here there is noise, and there's always noise. Cars out on the freeway close to where the seismometer and the little vibrations come through. But when a P wave comes through, you'll see a clear change in amplitude. And then it'll keep recording. Now the P wave just keeps going on and on and on and starts dampening out. What you're looking for is the next big change. So here's the change, and here's where the next big change is, right there. You can see all of a sudden, boom. And it isn't the biggest change in this sequence, but here we have a change in amplitude. That's when the S wave arrives. And these are the two most important things for our study in terms of finding the distance from your recording station to the focus of the earthquake. Remember from our lecture that the focus is the center point of the area of rupture along a fault plane that generated an earthquake. The epicenter is the point directly above it on the Earth's surface. So the epicenter is a geographic point. It is not where the earthquake occurs. Earthquake occurs at some depth. The epicenter can also be thought of as the closest place on the Earth's surface to the earthquake, but it's the geographic center point. Very commonly on a map, you'll see the epicenter shown with either a color coding or some way of showing the depth to the focus. That two components, the location on the Earth's surface and the depth of focus, gives you the three-dimensional location of the focus itself. Now, how do we get there? Well, the couple things you're going to note from a seismogram is the first arrival of the P wave. A lot of times it's shown as T for time, and then in small letters, P arrival, PA, and then TSA, the time of the S arrival. Those are the two most important time markers. The interval between them is referred to as the S minus P interval, sometimes the S minus P lag time, but that is the interval. There are two different ways to get this interval. Either you take the arrival of the S wave, the actual time of arrival, and subtract the time arrival of P wave, and you get so many seconds. That's referred to as the S minus P interval. That's why it's called S minus P. Or, more easily, you simply go to the recording, and because this is time, it's ground motion on the y-axis, the vertical axis, versus time on the horizontal or x-axis. So you can just count over the time. If you start at 0, and that's what we've done here. We haven't shown you the absolute time markers. We just said you start here. You look at the time in seconds, so you just count it over. This is 10, that's 20, that's 30, and there are 5 divisions, so it's 2 seconds. So we have 30 seconds, 2, 4, 6. So this would be 36 seconds. That would be your S minus P interval. The other thing to note is something called amplitude. Amplitude is a measure in millimeters on your seismogram of the ground motion. And that measurement in millimeters is from the still line, the 0 millimeter line, to the highest peak of the S waves that have come in. The highest peak, not the first one, but the highest one. Now, sometimes on a paper copy, that's hard to do. It's kind of a smear. You don't know where the center line is. So one of the cheats that my colleague Dr. Chikansky always likes to talk about is measuring, instead of measuring from the still line, the center line, to the highest peak amplitude of the S wave, measuring from the highest peak amplitude to its peak on the bottom, and then dividing by 2. That, on a paper copy, if you're having trouble figuring out where the middle mark is, if you take that tallest peak to its bottom on the other side, divide by 2, whatever it is in millimeters, divide by 2, then you will get your amplitude. And that's a lot of times a better way to get amplitude, but you should understand what amplitude is, right? It's from the 0 line up. It's that measurement. The other thing to note about working with amplitude is we're working with millimeters. If you're using a millimeter scale ruler, one of the issues is we're in the United States more used to the imperial system where you're dealing with inches, right? So this is unlike inches. Your metric ruler a lot of times will have a 1 mark on it. That 1 mark is 1 centimeter, which is 10 millimeters, or 10 millimeters in 1 centimeter. So always be careful when you're using a metric measurement system that you know what you're doing. Here on this, we can see that the amplitude is simply in millimeters. You don't have to worry about that. If you were measuring on the paper copy with a metric ruler, remember that the large ticks, the 1s, the 2s, the 3s, are centimeters. And other ways to think of that is 10 millimeters, 20 millimeters, 30 millimeters. So in doing that, what are we really looking for? There are a couple of elements. One is we're going to try to find the location of the epicenter of an earthquake. To do this, you need at least 3 recording stations where you know the S minus P intervals, and on a map, you are able to look at the distance. The other thing you need is a conversion from S minus P interval to how far you are from the focus or the focal distance. So let's talk about locating the epicenter of an earthquake, and we'll bring it into 2 steps. 1, determining the focal distance of an earthquake from your seismic recording, and then using 3 or more plots to locate the epicenter. So here's our sample seismogram again. In the S minus P interval, again, is here. That's the TPA, or the P arrival time. This is the TSA, or the S arrival time. You take the interval between, and then you go to a seismic wave travel time conversion. This is using travel time curves. Now I'm going to just show you there are 3 curves on here. There's the S curve, the P curve, and the S minus P curve. The S and P curve are plots. This is done empirically. That means for known earthquakes, it was timed. How long did it take for the P or the S wave to travel a particular distance? And in its original form, this is just a cluster of plots. And then a best fit line for the S wave and a best fit line for the P wave were put on. And now we've plotted them on the same scale. Why? We're saving paper, and they are 2 separate plots. The third plot is the S minus P plot. It's derivative. It's not a derivative the way we think of in calculus. It's simply derived from S and P. That is, if you were to take the distance here in time, the difference in time, I mean, and you just took that difference as so many seconds and replot it, it would plot to here. So you can see as this gets bigger, this gets bigger. Till you get this is big, that's the same as this. So we could just use the S minus P and try to fit between, but we've gone to the trouble of plotting a third curve, the S minus P curve. And what does this show? For the S curve, it's saying that it takes 6 seconds for an S wave to travel 20 kilometers. For that same distance, it takes 3.5 seconds for the P wave to travel 20 kilometers. So the difference between 6 seconds and 3.5 seconds is 2.5 seconds. Okay, here's 2.5 seconds. That makes sense? So that point plotted there says the S minus P interval of 2.5 seconds is equivalent of traveling 20 kilometers. So you take your S minus P interval and you're going to ignore the S and P curves that are here, and you're going to look at that derived curve, the S minus P curve. So for example, if you had a 4-second S minus P, you'd go 4 seconds on your time scale and draw a line all the way over, ignoring the first 2 curves, until you run into the S minus P curve. Then you would draw a line straight down, and that would give you a focal distance of 32 kilometers. That's it. So you would note the focal distance for multiple seismograms from multiple recording stations. If you have 3 or more, you can do something really interesting and approximate the location of the epicenter. And this is sort of shown here. I took this from a textbook I used to use. But the idea is, if you have 3 or more recordings, you can, on a scale map, take the focal distance and draw a circle around that focal distance. Draw a circle around that focal distance on a map to scale for that particular recording station. Then you do that for 2 other recording stations. Here it's showing Honolulu, Stockholm, and Manila. And you'll notice that if you just looked at Honolulu, which is the yellow line, and Stockholm, which is the blue line, they cross in 2 locations, right? One on the opposite side of the Earth and one over here. What lets you know that the epicenter is over here is when we draw the line in from Manila, the circle around Manila, they all intersect here. Now here it shows a point. In reality, because of the fact that we're actually using average travel time curves for the crust, we don't usually get a point. What we get is a little triangle of intersection. You don't shade that in. That doesn't mean it. You're looking for a point. So you put the point in the center of that little triangle, and that is the epicenter. And there's nothing more to it, right? And so this is using 3. In reality, we do this digitally. We do it by computer now. We use thousands and thousands of data, and we get a fairly good look at what the epicenter of a particular earthquake is. The averages tend to drop out, and you get a much more refined and fairly accurate location. The next task after doing a location of the epicenter of an earthquake, and actually that's 2 tasks, right? The first task is using any particular seismogram and your travel time curves to figure out the focal distance of an earthquake, using 3 focal distances to figure out the plot of the location of the epicenter of the earthquake, and then that's followed by determining the magnitude of an earthquake. And we're looking at magnitude. Again, we've talked about magnitude in lectures, so if you're having trouble understanding what we mean by magnitude, please go back to the lecture and make sure you're up to speed on magnitude before proceeding. But to figure out the magnitude of an earthquake, you need 2 things. One is you need to know the distance, the focal distance of your recording and your recording station from the earthquake that you're trying to determine the magnitude of, and then the amplitude. That's the amount of ground motion. Understand that if you're right next to the earthquake, the ground motion is going to be big, the amplitude is going to be big. If you're 100 kilometers away, the amplitude is going to be less. So what you record as an amplitude is a function of 2 things: focal distance and magnitude of the earthquake. Magnitude is a measurement of ground motion at the area of rupture. So we're looking at ground motion, but we know the distance. How do we know the distance? We already used the S minus P interval to figure out the distance. So what we're going to do now is look at the amplitude. Now we can only do this with a recording instrument, a seismometer, that has been calibrated. How's it been calibrated? It gets a lot of data from known earthquakes, and we look at what the magnitude is and the distance versus the amplitude. After that's done, we can construct a nomogram. A nomogram is only good for that particular station, because a nomogram for another station will be different. But once we work with a nomogram, we can do something like this. So here's an example. We figure out from our seismogram that the distance to the focus of an earthquake is 20 kilometers. How do we know that? That's S minus P interval converted from the travel time curves to figure out focal distance. So it's 20 kilometers away, and what we do then is we mark the 20 kilometers. Then we look at the amplitude. How do we get the amplitude? Measured in millimeters right on our seismogram. And on a particular seismogram for this example, the amplitude was 20 millimeters. So you draw a line on the nomogram between the 2. From 20 kilometers, that's the focal distance, across the magnitude bar to the amplitude. Where it crosses the magnitude bar, where that line crosses, that's the magnitude. In this case, it's a magnitude 3 earthquake. If you had a 20 millimeter amplitude, but your focal distance was 300 kilometers away, then your magnitude would be more like magnitude 5.5. Right? So remember, there's a function when you look at your seismogram. How big the ground motion is where you are is a function of how big the magnitude of the earthquake is and how far away you are. So these are the elements that you need. You have 2 options in this week's lab. This is the only time you have 2 options, but there is an online version called the virtual earthquake. If you do the virtual earthquake, make sure you follow the instructions I gave you, go to the link, and just work through the virtual earthquake. It is a really quick way to get through this, and you only have to do one of these 2 options. If you do that option, you send the virtual earthquake certificate to me. It'll ask what your instructor's email is, and you'll see I gave it to you in the instructions. You also tell them what your name is. You need your full name. Please don't just say Chuck, because I might have 5 Chucks in the classroom and you may not get credit for the laboratory. Your full name, the institution, Anza College, and then it'll ask for your instructor's email. You can also give them your own email. You can get a copy of the certificate for yourself, but I need the certificate to give you credit. So make sure my email shows up in that. Let's say you don't want to do that, or for some reason it doesn't work on your device. You try to go in, I can't do the virtual earthquake. Please don't send me an email. Instead, just do the second option. The second option is a paper copy of a particular exercise with an earthquake in the Bay Area. Either of these work. Don't do both. It's very confusing to me and also don't load your certificate back up as a submission in the system. If you do the virtual earthquake online, then all you have to do is make sure that the certificate is sent to me, and sometime next week I'll catch you up. It may say, it's late. You're not late. I just haven't put it in yet. I wait until they're all sitting in my inbox, right? So I have a special inbox that takes your certificates and I can work with them. You only have to do one lab. Don't load up a lab if you've done the other. If that makes sense, you choose one. If you choose the second one, then you do want to do a laboratory submission just the way you did for topographic maps. And that's kind of how that works. So good luck with the exercise. If you have any issues or need to talk to me, please send me a message through Canvas messaging. And otherwise, good luck with the lab.